All right, moving on to number 10. Here we are given f of x is a function of natural log, and we want to write the linearization of f at x equals 1. So let's go ahead and remind ourselves of the formula. The linearization formula is L of x equals f of a plus f prime of a times x minus a. And this is really the a value, and a value is just the value for x. So we're going to, for part A, we're going to find that the function at this x value, so let's plug in 1. 3 times 1 is 3 plus 1, so that's the natural log of 4. L of 1, I'm sorry, L of, let's say this, L of x is the natural log of 4 plus f prime of a, so that requires us to take the derivative. Let's take the derivative over here. F prime of x is going to be the derivative of natural log, which is 1 over u, and use what you're taking the natural log of, times the derivative of u, so the derivative of 3x squared is 6x. So basically it's just 6x over 3x squared, and so f prime of 1, we're going to plug 1 in here, is going to be 6 over 4. You can write it as 6 over 4, or I'm going to write it as 3 over 2. So that's 3 halves x minus a, which is 1. All right, we're going to use this to approximate f of 1.2. So L now of 1.2 is going to be natural log of 4, that doesn't change, plus 3 halves. The only thing we're doing is plugging in 1.2 for x. So 1.2 minus 1, so that's going to become 0.2. And if I go ahead and plug that into my calculator and get kind of a number for that, we get the natural log of 4 plus 3 halves times 0.2, which is really the same thing as 1/5. So that's really the natural log of 4 plus 3 over 10. All right, they want to know, is the approximation too large or too small? And this really has more to do with what the graph looks like in the first place. So let's think of this. A natural log graph, we should know, looks something like this curve, right? It's got kind of an asymptote going on right around when x equals 0. And I know that it's moved a little bit because it's not natural log of x, but the curve is not going to look any different. So any tangent line that we draw, if I draw a tangent line right here, if I make that tangent line red so we can kind of see it a little better, any tangent line we draw is going to be on top of the curve. And so any approximation is going to be above the curve. So that's why this approximation is actually going to be a little bit too large for us. And that's because the curve itself, the reason is the curve itself, f of x, is concave down. And so the tangent line is on top of it. All right, let's move on to number 11. Find an expression for dy dx. This is your implicit differentiation because we do not have a function solved for y. So I'm going to take the derivative of each part. So I've got derivative of x squared is 2x dx dx. I don't have to write it. Plus, this is a product. So it's x times the derivative of y, which is dy dx, plus y times the derivative of x, which is dx dx, plus 2y times the derivative of y, which is dy dx, equals 0. Okay, so I'm going to group my dy dx on this side. Everything else I'm going to subtract to the other side. So my dy dx terms I have left are x plus 2y. And everything else has gone over, so this is going to be negative 2x minus y. Finally, I get dy dx is equal to negative 2x minus 2y over, not 2y, I apologize, negative 2x minus y over x plus 2y. All right, B and C are actually using this value to find points on the curve. So we want points on the curve where the tangent is horizontal. A horizontal tangent means the slope is 0. Well, this is our value for the slope. if we set the slope equal to 0, then that means the numerator of our slope is going to equal 0. So 0 equals negative 2x minus y. This tells us that y is actually equal to negative 2x if I add y to the other side. So we want points on our curve where y is equal to negative 2x. Let me repeat that. Sorry, bring the y over, negative 2x on that side. So we're going to go back to our curve. And this is the formula for our curve, right? And we're going to replace all of our y's with negative 2x's. So we have x squared plus x times y, which is now negative 2x, plus y squared, so this is negative 2x squared, equals 27. And we're going to solve for it. So we've got x squared, x times negative 2x is negative 2x squared. Negative 2x squared is plus 4x squared equals 27. X squared minus 2x squared is negative x squared plus 4x squared is 3x squared equals 27. If I divide by 3, I get 9, which means x is equal to plus or minus 3. All right, plug it back in, and those will give your y values. So, or in fact, we can actually just use this. If y is equal to negative 2x, then the point would be if x is positive 3, then y would be negative 6. And if x is negative 3, then y would equal negative 2 times negative 3, which is positive 6. These are the 2 points on the graph where we have a horizontal tangent. All right, one last step. We want to know where the tangent is vertical. And this means the slope is undefined. And basically, in terms of a slope, that means that dy dx is equal to some number divided by 0. Okay, so that means this part, x plus 2y, now equals 0. All right, best one to solve for here is probably x equaling negative 2y. We go back and we do the same exact step before. We plug it into the curve because we want points on this curve. And now I'm going to replace all the x's with negative 2y's. So I get negative 2y squared plus negative 2y times y plus y squared, and that has to equal 27. Negative 2y squared is 4y squared minus 2y squared plus y squared. We get 2y squared plus y squared equals 27. 3y squared is 27. So therefore, we can see again, we get the same answer. Y is equal to plus or minus 3. When this happens, we go back to our x and plug it in. When y is positive 3, x would be negative 6. When y is negative 3, x will be positive 6. All right. Final question for this one. Number 12. Given y equals 4x cubed minus x squared plus 5, find the average rate of change. So average rate of change is your f of b minus your f of a over b minus a. Okay, so we're literally, and b and a are these two values. And if you switch them, it doesn't actually really matter. We just normally make a smaller, b bigger. So the function, if I plug in negative 1, I've got 4 times negative 1, so that would be negative 4, minus negative 1 squared. Negative 1 squared is 1, so minus 1 plus 5, minus, okay, let's plug in 2. If I plug in 2, I've got 4 times 8, so that I believe is 32, minus 2 squared, which is 4, plus 5. All right, all over. Ooh, and I mixed it up. I did f of a minus f of b. So that's fine. I can switch these around. A minus b. So that's negative 1 minus 2. And it's okay as long as you're consistent. It doesn't matter this order as long as you are consistent. Okay, so what are we going to get? Negative 4 minus 1, I believe is negative 5 plus 5 is 0. So that becomes 0. Minus, we've got 32 minus 4. 32 minus 4 is 28, add back the 5, you get 33 over -1 minus 2, which is -3. So negative 33 divided by -3 is positive 11. That's our average rate of change. Find the instantaneous rate of change, and this is actually, instantaneous rate of change means f prime of 1, so the derivative. So let me find the derivative of this now. F prime of x is equal to, bring down the 3, so that's 12x squared minus 2x, and the 5 goes away. Now go ahead and plug in that 1. 12 times 1 minus 2 is 10. Now the instantaneous rate of change and the average rate of change might equally cut each other, or in this case, they don't.